Hey, my friends, you ready for video number 7 in our chemical reaction adventure? Gonna get into something you probably won't see on, at least with me, exams or quizzes, but you definitely will see in lab, fairly common in a real life scenario, where we can have simultaneous equations. This kind of goes hand in hand with the sequential equations we did and combining equations. Really, those be in one lecture, but I'm trying to keep the videos a certain length, so we'll split it into like part A and part B. This actually, if we look at the last video when we talked about the two sequential reactions, consecutive reactions, where the magnesium reacted with nitrogen as a side reaction, producing magnesium nitride. When if you're combusting it, you should get the oxide, like magnesium oxide or aluminum oxide, but you can get the side reaction, an unintended reaction due to reaction of nitrogen gas and oxygen gas at the same time when you're heating it up and combusting with air. You're getting the oxygen from air. So you can get these side reactions that are unintended. So two reactions are happening at the same time or simultaneously. That sometimes that's something we want to happen, and sometimes that's something we don't want to happen. So where can we find that? Very commonly when you have an alloy. Remember, an alloy is just a mixture, a homogeneous mixture of two or more metals. Brass and bronze and all those things, pewter. You might have a lab where you're taking, instead of a pure metal, you take a metal alloy, react it with acid, convert that into hydrogen gas. Great gas lab. You collect the hydrogen gas and use I haven't done that yet, but we use gas law mathematics to work backwards to figure out the original mass of the metal or the alloy in this case. So if we have an alloy that's two or more metals and they all react with this acid, you have these multiple equations. If you have two metals, they're both reacting simultaneously. Or you could have a side reaction like the nitrogen coming in with air as well as the oxygen. How do we treat this mathematically? Well, you got to treat them separately. Right? Got to keep them separated. So if I have an alloy with two metals in it, I'm going to identify those two metals and ideally what percentage that alloy is of those metals, and do an equation for the first metal, say reacting with the acid, and then separately the second metal reacting with the same acid. Do the stoichiometry for the first metal's equation, solve for example, the amount of hydrogen produced, and then in a whole nother whole nother mathematical problem, do the other metal, figure out the amount of hydrogen produced. And then what I can do is just, once I'm in the same thing, once I have moles of hydrogen or grams of hydrogen, I can combine those together. So we're going to treat them separately when we're doing the mathematics. Let's do a problem. You may or may not run into this on some homeworks or some labs. It's a little bit more advanced, but once you see how it's done, it's not harder per se, it's just longer. Instead of this one nice stoichiometry step, you're going to have two separate ones, kind of like limiting reactant problem. You got the two separate stoichiometries, and then in a third step, we're going to add the answers together, and you may even have a fourth step depending on what unit you're going towards. Longer, but not more difficult. Let me throw one up on the board for you. All right, here's something you might run into in a lab. Let's say you get some metal alloy. Right? We know that's made of zinc and aluminum. And we know the percentages. We know this alloy is 25.4%. I should say by mass. Should tell you whether it's mass or volume. 24% zinc by mass. That way we know the units there. So we would have probably made the assumption it was 25.4% zinc by mass, but it's better to be clear in your statements. And so it's 25.4% zinc by mass, and then the rest is aluminum. We can solve for how much, right? Just subtract it from 100. And we weigh out this sample, maybe put it on an analytical balance, and it's 0.9254 grams. So we got this alloy, we weigh it out, it's 0.9254 grams. We know the percentage of zinc, we know the rest of it's aluminum, and we react it with some hydrochloric acid. Concentration not important at this point, and it's excess hydrochloric acid solution. So we know every atom of aluminum and every atom of zinc are going to react and go bye-bye. That's the limiting reactant. How many grams of hydrogen gas can be produced? So we've got two metals in here. We've got zinc and aluminum. So what we got to do is figure out what's the percent of aluminum. Look at the two equations, right? We've got zinc reacting with hydrochloric acid, and we've got aluminum reacting with hydrochloric acid. So we need the two separate equations, and we need to write and balance those so we can get the stoichiometric mole-to-mole ratios. And then what we're going to do is do two problems. We're going to do the zinc stoichiometry problem, how much hydrogen gas is produced, and we're going to do the aluminum problem, how much hydrogen gas is produced, and then we just add those together. That's a 2-for-1 special. So nothing new, but there's a lot of cool stuff in here. So first, let's figure out what the percentage of aluminum is. You could probably do this in your head, I would hope. Hope. Right? So we know the percent of zinc is 25.4. And we know there's only two metals, so if we add them together, we know the percent of zinc plus the percent of aluminum should be 100, right? Very common. We did this with isotopes back in one of the earlier chapters. So we can calculate the percent of aluminum. That will just be 100 minus the percent of zinc. So we're going to go 100%. That's an exact number. Minus 25.4. And so pop that in your calculator, you should get 74.6% aluminum. Just do that in your head. Just pop it on your calculator. You don't have to show me that. All right. Now, we're going to set those up. Let me show you how to set these up, and then we'll do the equations on a separate board. We'll do the equations here. Let's figure these out, because we've gone through percentages before. I don't need to repeat it here. But when you look at a percent, again, that's a part per 100. So 25.4% by mass zinc means you have 25.4 grams of zinc for every or over 100 grams of the alloy. And the aluminum would be 74.6 grams of aluminum over 100 grams of the alloy. That's how we take percentages and set them up as conversion factors to go from the part, the metal, to the whole, the alloy. Right? We did that before. So let's look at the two equations. So we've got zinc, and we're going to react that with hydrochloric acid, right? So let's react that with hydrochloric acid. Single replacement reaction, so we're going to get hydrogen gas plus zinc chloride. So zinc will always be a +2, right? So if zinc's a +2, it'll end up with 2 chlorides. And then if you look on your solubility chart, that's not soluble. Plus hydrogen gas. And then we got to balance this bad daddy. So zinc, 2 chlorines. So let's pop a 2 there, 2 hydrogens. That wasn't too bad. Not bad at all. Let's do the same one, but let's do aluminum. Remember, they're both metals will be reacting simultaneously when we add the hydrochloric acid. So let's look at the second equation. Same concept. Aluminum plus the hydrochloric acid, same idea. We're going to get hydrogen gas and then the aluminum chloride. Aluminum's a +3. So we're going to get AlCl3, which is also soluble. We're not going to get a solid or precipitate out of that. So write your products. Now let's balance it. We've got 3 chlorides here and 1. So if I pop a 3 here, 1 aluminum, 3 chlorines, I got 3 hydrogens and 2. Oh, man. So 3 here, that's odd. 2 is even, so I need the common multiple between 3 and 2, which is 6. So 2 times 3 would give me 6. And 3 times 2 would give me 6. So now I got 6 hydrogens, but I messed everything else up. Now I got 6 chlorines. So 2 times 3 gives me 6 chlorines, gives me 2 aluminums. That one was a little harder than the zinc. Now I can do this. See if you can do it on your own. Take your mass of alloy for the zinc, convert that to the grams of zinc using that percent. And then go from grams of zinc to moles of zinc to moles of hydrogen, right? And then take the mass of the alloy, convert that to mass of aluminum using the percentage of aluminum. And then once you got grams of aluminum, go to moles of aluminum. And then you can go to moles of hydrogen. Note this is a 1-to-1 mole ratio for the zinc and a 2-to-3 ratio for the aluminum. That's why you got to do them separately. And you'll get moles of hydrogen gas from the zinc, moles of hydrogen gas from the aluminum. That's the same thing, right? You got a pepperoni pizza plus a pepperoni pizza. You got to have the same. You can't add a pepperoni pizza to an artichoke pizza. I need pizza now for lunch. Add those together, and you get total moles of hydrogen. Once you got total moles of hydrogen, you can convert that to grams, and then to, was I a booger? Let's see. Yeah, I asked for milligrams, so I added an extra metric conversion. See if you can pop that out. I'm going to erase this and do these in turn. Let's do the zinc one first and then the aluminum one. Then we'll add them together. How's your first part of this going? It's like I said, it's pretty much a 4-step problem. Get the moles of hydrogen from the zinc. Step 1. Step 2, get the moles of hydrogen from the aluminum. Step 3, add those together to get the total moles of total moles of hydrogen. And then step 4, convert moles of hydrogen to grams and then to milligrams. So here's one. Let's see if you got the same thing. So I rewrote, you didn't have to do this. I rewrote the balance equation for the zinc reacting with hydrochloric acid. Let's take the 0.9254 grams of the alloy. That's our mixture. Let's use the percentage as a conversion factor to go from grams of the mixture, the alloy, to the grams of the part we're interested in. We're going from the whole, the alloy, to the part, the zinc in this case. And we know it's 25.4% zinc by mass, which means if I assume 100 grams exactly of the alloy, there'd be 25.4 grams of zinc. Right? That's how a chemist sets up a percentage as a conversion factor. So that allows me to cancel out the grams of the alloy. See how that cancels out there? Boom, boom. Now I'm in grams of zinc. So look on your trusty periodic table, depending on, you get a different periodic table, you might get a different value. So zinc, I have 65.382 grams per mole. So there's the 65.382 grams of zinc per mole. Grams of zinc cancels out. Now I got moles of zinc. I can go over to the moles of hydrogen. I got a 1-to-1 ratio. Well, that's terribly boring. Moles of zinc cancels. That leaves me moles of hydrogen. Remember, I got to get to moles of the products so that I can add those together. 4 significant digits here. That 100 is exact by definition. The percent, though, the 25.4 is not exact. That's 3 significant digits. I got 5 sig figs in my atomic mass. Mole ratios are exact, so I'm good to 3 significant figures. I get 0.00359. Vertical dash line, 50 moles of hydrogen. That's from just the zinc in that alloy. I'm going to get more moles of hydrogen from the aluminum. So pause the video and see if you can do the aluminum one. All right, so I'm going to pause it, write up the equation, and let's work through and see if we get the same answer. Let's compare answers, my students. Good students of mine. Or casual observer, if you're not one of my students and just enjoying videos, because you've got nothing better to do on a Saturday. Let's take the mass of the alloy. So these look, from a distance, they look exactly the same. The only difference is the molar masses, the percent, things like that. So we take the exact same mass of the alloy, that's the whole, use the percentage of aluminum, which we calculated earlier, 100% minus the percent of the zinc, which is 74.6. So if for every 100 grams of the whole, the alloy, the mixture, there would be 74.6 grams of the part, the aluminum. And we did the 25.4 for the zinc, but the 74.6 for the gram, assuming I did my math right. Now we got grams of aluminum. Use the atomic mass of aluminum. Some of you are like, man, there's so many decimal places. Wah! Call the wambulance. All right, so aluminum, holy moly, 26.981538. Who got so many decimal places there? I figure it takes you, 0.5 of a second to write that down. You might as well just do the whole darn thing. So 26.981538 grams of aluminum per mole. And then we've got 2 moles of aluminum producing 3 moles of hydrogen. So different mole-to-mole ratio, right, than the zinc. 4 significant digits in the mass. That 100's exact. 3 significant digits in the percent. a whole truckload in the atomic mass of aluminum, and then that's exact. So again, we're good to 3 significant digits. So I get 0.038378 moles of hydrogen, good to 3 significant digits. Pop my dash line there. So step 1, moles of hydrogen from the zinc. Step 2, moles of hydrogen from the aluminum, or whatever metals are in it, the mixture, or whatever mixture you got. Now I can add these. See, we got pepperoni pizza, moles hydrogen, pepperoni pizza, moles hydrogen. Now we can add those. Same units, same species. So take the 0.003595 moles of hydrogen, good to 5 decimal places, and add that to the 0.038378 moles of hydrogen, good to 4 decimal places. That'll get you the total moles of hydrogen, good to 4 decimal places. I'm going to do that on the next board, and then convert that into milligrams of hydrogen. Do it! How'd you do with your total moles? So I took the total moles of hydrogen, again, is the moles of hydrogen from the zinc plus the moles of hydrogen produced from the aluminum. So I took the value from the zinc plus the value from the aluminum and added them together, limited to 4 decimal places. So I get 0.041973, good to 4 decimal places, moles of hydrogen total. You don't have to write that equation up on the board, but it allows you to see if you're reviewing this where that comes from. So that's kind of step 3. Again, step 1, how many moles of hydrogen from the zinc? Step 2, how many moles of hydrogen from the aluminum? Step 3, add them together, you get the total moles of hydrogen. And now step 4, convert that to whatever units were asked for in the problem, in this case milligrams because I was being a boogerhead. I didn't leave it in grams. We got to go to milligrams of hydrogen. It's a gas. It's not going to weigh a whole lot, right? Now, ideally, when we get to gas laws later, I can have you calculate the volume of that given a temperature and pressure, but that's in your future. Here we go. So let's get the milligrams of hydrogen. So let's take this answer, bring it down, 0.041973 moles of hydrogen. So let's figure out and now hydrogen's diatomic, watch out for that. So there's 2 of them. So we need to take the atomic mass of hydrogen, the 1.00794, and add those together, and then we're going to get to 5 decimal places. So add them together, I get 2.01588, isn't that right? So moles on the bottom. So for every mole of that element, there's 2.01588 grams of hydrogen. So that's the molar mass of the diatomic, that little bugger. Cancels out, and we wanted milligrams, right? So 1,000 milligrams per gram. So for every gram of hydrogen, there's 1,000 milligrams of hydrogen. Boom! Sound effects optional. Moles hydrogen cancel, grams hydrogen, so I'm left with milligrams of hydrogen. 4-step process. You're going to see this when we do titrations later. If you do back titrations, you got multiple acids, or if you have a situation where you have multiple bases. So we'll run into this 4-step process quite often. All right, I got 3 significant digits here in my total moles. I've got 1, 2, 3, 4, 5, 6 in my molar mass, and the metric conversions are exact. So I'm limited to 3 significant digits. I get 84.6. There's my 3 sig figs, so let's do a vertical dash line. Add 2 more. After that, you can add as many as you want, but do at least 2 for me. Looks like that's closer to 84.6 than 84.7, so don't round it up. Right, that's less than 5, so it stays as 84.6 milligrams of hydrogen. So that was a lot more involved problem than our simple stoichiometry we started the chapter with, but you can just see it's the same principles applied over and over and over, just with a new bag of tricks. So we've covered sequential reactions or consecutive reactions, how to deal with those by doing consecutive stoichiometry steps or combining those equations into one and getting rid of the intermediate species. And then we looked at what happens if you have simultaneous equations. You got to treat those separately and then add them together. You can do it, my friends. Yeah.